For the design of T and L beam, these are the basic steps. In the design, the following data will be given: loads, moments, FC prime, Fy, length of beam, roof slab thickness or the thickness of flange. Then we have to calculate the dimensions of the beam width and depth, and second, area of steel, bar bending schedule. So these we will calculate. First of all, select trial dimensions of the beam BW and H, nearly same as for used for the rectangular beam. Okay, we will first of all assume BW and H. Then calculate the effective width B. On the left and right side there are slabs, so from the given data we have to calculate the effective width. Step 3, assume the neutral axis to be at the junction of flange and web. Means we will assume that neutral axis lies at the flange and web junction. Means A1 is equal to beta 1 HF. Then we will calculate the area of steel. That is the basic formula for the singly reinforced beam. Mu over 0.9 Fy d minus A by 2. Moment will be given, effective depth we will have. So then we will calculate the area of steel. We will perform the trial, and then we will again calculate the A. And if our assumed value that the neutral axis at the junction is less than or equal to beta 1 HF, means our assumption is correct. The beam will be designed as rectangular section. Means if the A is within the flange, so we will design as a rectangular section, and if our A is greater than beta 1 HF, then the beam will be designed as T beam. So first of all we will calculate ASF. Okay, all the data we have, ASF will be calculated, and from the ASF moment capacity for the flange portion is calculated, 0.9 ASF Fy d minus beta 1 HF by 2. Then the moment capacity for the web will be calculated, total moment minus the moment capacity by flange, MW. Then from MW we will calculate ASW. Then we will put in the formula of A, and then we perform the trial until the AS are nearly close answers. After performing 2 to 3 trials, then we select ASW. The total steel will be provided ASF plus ASW, AS calculated previously. Then we will calculate the rho W, means area of steel in the web, divided by BWD, means width of the web. Then we will check for the minimum and maximum steel. Then at the end perform detailing and make sketches. Here is an example. Design a T-beam to be used as interior simply supported beam of span 5 meter. The slab panels on both sides of the beam are 3.5 meter by 5 meter, and the factor slab load is 15 kilonewton per meter square. That is the factor the load is given. FC prime 17.25 megapascal, Fy 420 megapascal. Here is the data. Width of the beam 300 millimeter, height of the flange 125 millimeter, section depth is given H 575 millimeter. That is trial. You use SI reinforcing bars designed for given loading. Means first of all we have to calculate the total load, then we have to calculate the moment, and then we will go for design. That is the first case. In the second case, from the loading already moment is given. If the moment is this, calculate the area of steel. Here is the beam arrangements. Okay, here is the length of the beam 5 meter, and the slab on the both sides of the beam are present. Okay, and this beam will be designed as a T beam. And on the right side that is also 3.5 meter, and on the left side that is also 3.5 meter. Example 4.4, that is the same example for the design that I have shown in the slide. Design a T-beam, interior simply supported beam, that is a beam of span 5 meter. The slab panels on both sides of the beam are 5 meter by 3.5 meter. This side the slab panel 5 by 3.5. This side the slab is also 5 by 3.5 meter. The factor slab load, that is 15 kilonewton per meter square. Okay, and then we have to multiply with the effective weight, then equivalent weight, then we will calculate the UDL. FC prime 17.25, Fy for 20 megapascal, height, width, and HB 575 millimeter, means the depth of the section of the beam. Use SI bars. This slab is on the compression side. For the first case design for the given loading. Second case, if the moment is 1000 kilonewton meter, then we have to design for that. First of all, for first case, data is given Ly, that is 5 meter, Lx in this shorter span, that is 3.5 meter, factor slab load 15 kilonewton per meter square, HB height of the beam 575 millimeter, effective depth, that is H minus 75 millimeter by assuming 2 layers of steel, 500 millimeter, BW width of the web 300 millimeter, thickness of flange 125 millimeter, FC prime 17.25 megapascal, Fy for 20 megapascal. Okay, first of all, factored self weight of the beam. Okay, 1.2, that is the load factor. Width of the beam, that is 300 millimeter divided by 1000, and height of the beam 575 minus 125. We are subtracting this flange thickness. Why? Because the load of the slab is also have the flange thickness. So we will take the only the part that is below the slab. 575 minus 125 divided by 1000 multiplied by concrete density multiplied by 9.81 divided by 1000 to convert into Newton. So we got the answer 3.82 kilonewton per meter, the factored self weight of the beam. Okay, we have calculated the weight of the beam. Now to get the equivalent width, to multiply this 15 factor slab load, or Lx over Ly, that is 0.7, and for the interior beam equivalent width, that is 1 minus r square over 3 into Lx. So we got the value of 2.93. Now we get the factored slab load 2.93 multiply 15, we got the UDL value 43.95 kilonewton meter per meter. So the total load is 43.95 plus beam self weight, that is 3.82. So we got the total load, that is 47.77 kilonewton per meter. To get the moment, omega L square by it, for simply supported beam 47.77 into L square over 8. Okay, we got the moment value 149.3 kilonewton meter. Now we calculate the effective width for the T beam. To calculate the effective width is the smallest of the following. Okay, or of the three. First criteria is ln by 4 plus bw. Ln by 4, that is our span length, that is 5 meter, that is 5000 millimeter divided by 4 plus bw. The bw is the central web thickness. So 5000 divided by 4, we got the answer 1550 millimeter. Second criteria, 16 hf plus bw, 16 times 125 plus 300, the answer is 2300 millimeter. bw plus 0.5 span spacing on the left side, 0.5 span spacing on the right side. You have seen that on the both side this spacing is 3500 millimeter. So 3500 millimeter divided by 2, half span from this side, half span from this side. So here bw 300 plus 0.5, due to symmetry 3500 minus 300, that is the span spacing, cleared span spacing. So that's why subtracted 300. So multiply by 2 because spacing is same. Okay, so half from one side and half from one side. So we got the total value 3500 millimeter. So minimum of 3, that is 1550 millimeter. So effective width will be 1550 millimeter. Okay, now for the design, first of all we assume that our A is equal to beta 1 HF. So beta 1 0.85, H is 125. So we got the 106.3 millimeter. Then we will calculate the area of steel trial. Mu 49, that is given. Moment calculated 149.3 multiplied by 10 by 6 and 0.9 420 500 divide minus d minus a by 2 106.3 divided by 2. We got the area of steel 884 millimeter square. Then we will again calculate the A, revise AS from the previous step 884. So we got the A value 16.3 millimeter. We again perform the trial, put the A value in this equation, and then again calculate the value of area of steel. Okay, here. Okay, again perform the trial, we get the value of A and new value of AS, and you can see the value of A is lies within the flange. Neutral axis lies within the flange. So means our assumption is correct. And now we will check that is it our member is going for tension control. So we got the value of AL beta 1 3 by 8 D 0.85 0.375 into 500 59.4 millimeter. So our A value is less than this, that is tension control. We will use 0.9 value. Now rho W I will calculate, that is area of steel 802 millimeter square after performing trials, divided by BWD. BW 300, D is 500 millimeter, and the value I got 0.00537, and compare with the rho minimum. So rho minimum 1.4 our Fy, that is rho W minimum. So our rho W is greater than rho W minimum, so that is okay. So area of steel 802 millimeter square, 3 number 20 bars will be provided. Okay, so SI reinforcement is used. Okay, so now the detailing of this case 1. Okay, you can see the 300 millimeter total height of beam, that is 575 millimeter, width 300 millimeter, and you can see stirrups are entering into the slab. Okay, and 3 number 20 bars are chosen, 1 bar is curtailed, and 2 bars entered into the sports, and 2 number 15 bars are used at the hanger. Tie spacing number 10 at 250 millimeter center to center assume, because we didn't perform the shear analysis. So from shear analysis we got the stirrup spacing, so that we will see in the next lectures. Okay, that is the cross section and that is the longitudinal profile. Case 2, moment is given 1000 kilonewton meter. Same, we will assume A is equal to beta 1 H 0.85. Then we will calculate the trial AS. Okay, mu over 5B Fy D minus A by 2. From the assume A, we get the trial AS 5920 millimeter square. Then we will again put the value in A in the basic formula AS Fy over 0.85 Fc prime B. Then we got the value of A. Then we calculated the value of C, A over beta 1 128.7 millimeter. So our value is greater than H. Neutral axis lies outside the flange. So we will go the next step. We will calculate the ASF 0.85 beta 1 H Fc prime over Fy B minus BW. We got after entering the data, we got the 4637 millimeter square. In the literature, the author have mentioned that if our A is less than beta 1, our height of the slab, then it will be designed as rectangular section. And here it is calculating the neutral axis depth A over beta 1. So both methods are okay. You can use either way. You can use the method of A and you can use this C for the neutral axis locations. So now I have calculated the ASF. Now I will calculate the moment capacity for the flange portion. 5B MNF 5b ASF Fy into d minus beta 1 H over 2. Okay, ASF calculated in the previous step. So the moment capacity MF will be 783.3 kilonewton meter. Balance will be used for the flange portion. So now for the web, 1000 minus 783.3, that more steel will be required. Okay, for the balancing of web concrete, compression concrete, 1000 minus 783.3, that is 216.7 kilonewton meter. Okay, now assume A, that is 110 millimeter, or you simply assume beta 1 H. Trial ASW will be calculated. MW, our 5B FYD minus A by 2. Now we'll use A by 2. Then again calculated A, ASW FY, our 0.85 FC prime BW. We are calculating for the BW portion. Then we got the A value. Again put the A value in the ASW formula. You will get ASW value 1305 millimeter square. You will again calculate the value of A, means again perform the trial, and up till when the answer are nearable, just like 1310 and 13057 millimeter square are nearable answers. So we have selected AS 1310 millimeter square. So total area of steel is ASW plus ASF 1310 plus 3637. So answer is 5947 millimeter square. So provided 12 number 25, 1 bar of 25 of SI reinforcement, that is 500 millimeter. So that provided steel will be 6000 millimeter square. So that is okay. Now for tension control checking, A beta 1 3 by 8 D, answer is 159.4 millimeter. So our A is less than, for we will use 5B 0.9. So here is the detailing. So here is the 12 number 25 bars, 4 in 2 layers and 4 in the above layer, and 4 up are curtailed. And here is the stirrups again assumed. Okay, and the spacing between the bars checked here. Total width of the beam 300 millimeter minus 2 times concrete cover minus 2 times stirrup minus 4 times 25 bars. Okay, and 3 spaces are between the bars, 1 2 3, so that's why divided by 3. So we got the spacing between bars, that is 33 millimeter. So greater than 25 millimeter, so that is okay. So that's all for today's lecture regarding design of T and L beam. Similarly, I have shown for the T beam, and for the L beam only the criteria of B will be changed, effective width will be changed, rest of the design will be same. So have a nice day.